Welcome dear students to this new video. So in this video today we'll be starting with a new chapter, that is CPU scheduling, where we'll be covering about the basic concepts of CPU scheduling. Then we'll be discussing about the scheduling criteria, and at last we'll be discussing about the various scheduling algorithms. But as far as this video is concerned, we'll be covering with the first two things, that is the basic concepts as well as the scheduling criteria. So let's begin with the basic concepts of the CPU scheduling. So if you see over here, so far we have read a number of times that our main aim is to keep the CPU busy so that we can have maximum CPU utilization. This is done with the help of multi-programming. So we have seen that process basically uh, switches between the CPU's time as well as the IO activity. That is, for certain span of time, the process executes with the CPU, and thereafter, when the need arises for some IO related event, it jumps from CPU's running state onto the waiting queue of the devices. So there is basically a cycle between the two things. That is, for every process there is more or less there is a CPU burst followed by an IO burst. So a cycle is basically over there where CPU burst is followed by IO burst, then again CPU burst, then again IO burst, and this process continues till the time the process terminates. So fine. So also we know that there should be a proper process mix so that the CPU can be utilized properly. That is, we should have a mix of some CPU bound processes as well as some IO bound processes, so that the system can work to its optimum utilization. When I'm saying system, I am referring over to here with regard to the CPU's utilization. In the ready queue, number of processes actually are waiting to gain the access of the CPU, and out of those waiting processes, uh, only one process is fetched at one time and is handed over to the CPU for execution. So see, in CPU scheduling, basically it is the process of determining, that is, which process from the ready queue out of all the waiting processes will be allocated to the CPU for its execution. So for this we are having a number of scheduling algorithms based upon which this decision is made regarding the selection of a process and forwarding it to the CPU for execution. So the algorithms includes, the first one is first come first serve, then we are having shortest job next, then we are having round robin, as well as we are having priority scheduling. Now different algorithms support different class of processes and favor different scheduling criteria. So we'll see this thing in the coming slides. Basically we can divide the scheduling into two categories. The first category is known as non-preemptive scheduling, and the second category is known as preemptive scheduling. Now as far as non-preemptive scheduling is concerned, basically once a process is allocated the CPU and that process is executing, the process keeps the CPU until its entire CPU burst time has elapsed. I mean to say over here that whatever burst time the CPU, whatever burst time that process was having, the process will continue executing with the CPU for the entire period of time, and any other process cannot forcefully get back the excess of CPU from that executing process. That is, the process which was executing will only release the CPU at its own will. When I'm saying will, basically it means it will continue with the CPU's execution for its entire burst time, or the CPU time. What is burst time? Burst time is the time for the time which the process needs to execute with the CPU. Fine. And process will only leave the CPU when it has terminated, or that process which was executing needs to perform some IO activity, so it jumps from running state onto the waiting state of IO devices. So depending on only these two situations, basically the process leaves the control of CPU. Otherwise, forcefully the gain of CPU access cannot be done by any other process if the scheduling is done in non-preemptive manner. On the other hand, in preemptive uh, scheduling, so basically, once the CPU has been allocated to a process will leave the CPU willingly or it can be forced out. Whereas in the previous case, it was only this part. That is the process will leave the CPU willingly only. Whereas in this case, it can be forced out also. So there are actually four possibilities over here. So if you observe those four possibilities, the first possibility is that the process will leave the control of CPU when it has completed its execution. That is, process needed CPU for, let's say, 5 milliseconds. So it continues there with the CPU for 5 milliseconds, and in between no other process came and tried to forcefully remove the this process from executing. So this process will continue there for 5 milliseconds, and suppose after that the entire task was over, so this process has terminated. So in that case, obviously it will leave the control of the CPU. That is, the process has completed its own execution in this stage. Second thing is that the process was executing, but in between, during its execution with CPU, it needed some IO related activity to perform. So for that, it switches from running state onto the waiting state of IO devices. That is, it itself, because of some activity in between, it itself is leaving the control of the CPU. That is, it is doing it voluntarily. So that is the another possibility when this processes leaving the control, but here the leaving of control is on voluntary basis. Fine. The third thing is that the third possibility is that uh, another process enters a ready queue when process P1 was executing, and this another process, let's say P2, was of higher priority. So as this process was of higher priority, in that case, the process which was executing has to leave the control of the CPU in between. When I'm saying in between, that means it has not completed its task. But because of this higher priority process, it has to leave the control of the CPU. So in that case, this P1 will switch back onto the ready queue, whereas P2 will gain the access of CPU due to its higher priority. So here the process is forcefully asked to leave the control, and this is permitted as the scheduling over here was preemptive one. Another possibility is that when a process switches from running to ready state because of time quantum. So suppose we were working in time shared environment, and in time shared environment each process is given equal amount of time in one go to execute with the CPU. So suppose P1 was executing and the quantum of time which was set for this system has elapsed. So in that case, P1 has to leave the control of CPU because its time period has elapsed. In that case, P1 again comes to the uh, ready queue and is waiting for its turn next time, so that it can get the access of CPU and can continue its remaining task. So when it is leaving the control of CPU, that means some other process will gain the access of CPU. So in this case again, it was because of the time has elapsed and the task of the process was not complete. So again, this is feasible because the scheduling pattern was preemptive in this case. Now let's discuss regarding CPU scheduler, that is how the scheduling decisions are taken. So let's see that. So we have read so far that it is the short-term scheduler basically which fetches the one process from the ready queue out of all the processes which are waiting in the ready queue, and the process which it selects is passed on to the CPU for execution. Now, as far as the queue over there is concerned, it is ordered in various ways. So, CPU scheduling decision may take place basically. Actually, when does this thing comes into picture? When does CPU scheduler executes itself to fetch a process from the ready queue and pass it on to the running state for CPU's execution. So this situation arises when switching from running state to waiting state. What I mean to say over here is, suppose process P1, P2 and P3 were there, and at time T0 process P0 was executing. So as of now process P0 is with the CPU, fine, and these three processes are in the waiting queue, or I mean to say in the ready queue, and are waiting for entering into the running state so that they can get the access of CPU for their further execution. So now, when will CPU scheduler come into picture? So there may be a stage that this process P0 which was executing needed some IO, need to perform some IO event. So in that case, this process will leave the control of CPU and will be in the waiting queue of the IO devices. So now at present the CPU is free, as no process is over there, as the one which was over here is in the waiting queue of the IO devices. So uh, now the short-term scheduler, basically it comes into picture. It selects one of the processes from over here and will pass on that process to the running state so that the CPU can execute that process. Second thing is, uh, suppose the process was running, I mean to say process P0 was running, and what happened over there is another higher priority process came over there, because of which process P0 has to be removed from the running state. So in that case, let's suppose when this process was executing at that time, P4 came, and this P4 was a process which was of higher priority. So as this process was of higher priority, in that case P0 was supposed to leave the control of the CPU in between so that P4 can be given access of the CPU. So in that case P0 shifts from running state onto the ready state and and it waits for its turn, so that whenever its turn comes it can continue its remaining execution. Fine. The third thing is that switches from waiting queue to ready queue. Now what happens over here? Suppose there was a process which was earlier in the waiting queue, fine, and it was waiting for some IO activity. And once that IO activity is over, that process is supposed to move into the ready queue. So let's assume that this process, which has just completed its IO activity, is of higher priority. In that case, again, the process which was currently executing, it has to leave the control of CPU in between so that this new process which has just entered the ready queue will so that it can gain the access of CPU. So so in that case also, because a process is to be brought from this place onto this place, so short-term scheduler basically executes. Then another possibility is that, suppose process P0 was executing and it has just completed its execution. So a new process from the ready queue is to be passed on to the running state so that CPU can execute that process. So in this case again, the short-term scheduler basically selects a process from the ready queue and passes it on to the running state, and the CPU executes that process. Now if you see over here, we have gone for the four stages. We have discussed the four stages, that is these four stages right now, and out of these, scheduling under stage number 1 as well as stage number 4, that is this one, and the last one is non-preemptive. Because why it is non-preemptive? Because in these two stages, it is not because of somebody that the process is leaving the control of CPU. If you see over here, the process which was executing, because of some IO activity has to leave the control of CPU, and nobody is forcing this process. It was this process itself who needs to perform some IO activity. So that is why it is leaving the control of CPU in between. So when nobody is forcing that, so obviously we are referring to that thing as a non-preemptive state, non-preemptive scheduling. Then if you see over here, the another one is when the process terminates. Process P0 was executing whatever task it was assigned, that entire task is over. So this process no more needs the CPU as it has finished its task. So this process terminates. So again, then because CPU is free, some other process comes for which the selection is made by the short-term scheduler, and that process comes and is given the access of CPU. So again, in that case also, P0 was not forcefully removed from executing with the CPU. It was because that process terminates. That is why the another process is coming for execution. Option number 1 as well as the option number 4, both of them, in both of them, the scheduling is basically non-preemptive, whereas all other schedulings are basically preemptive. So there are few issues which needs to be taken into consideration when such things are happening. When a process is forcefully removed in between, so suppose that process is working on some shared data, and as of now that activity has not yet completed, but process p0 was forcefully removed. So in that case the updation was pending. Someone is trying to read the incomplete data, so this will lead to a inconsistency in the system. Then suppose the system was working in the kernel mode, where the user has requested some system call to be performed, where in kernel mode that exercise was being done. But because this process was I would say forcefully removed, in that case also this will lead to some sort of issues with the system, because system again will be in some sort of inconsistent state. Fine. Then another option is over there, where suppose that some interrupt occurs during some crucial OS activity. Some OS operation was going on, but in between, before that operation could have been completed, some interrupt has occurred, because of which that OS operation was pending, and this interrupt was executed first. Again, this might lead to some sort of inconsistent or unstable state. So such things needs to be considered during the preemptive scheduling. So there is one more thing over here which is referred to as a, I would say, dispatcher module. And that dispatcher module is something which basically provides the control of the CPU to the process which has just entered into the running state. So it gives the control of the CPU to the process which is selected by the short-term scheduler. So as far as this exercise is concerned, it involves few things. So we have already read about this part in the previous process scheduling part. That is because some process which was already executing, so first of all we need to save the state of that process, and also we need to load the state of the new process. We need to reload it so that the CPU can start working on that process. And this involves like jumping to the proper location in the user program to restart that program. Basically, suppose that process was earlier also executing and it was stopped in between, and now it has to continue from the place from where it left. So in that case, the execution has to begin from the from that proper location from where it left. So all such kind of things are involved, and where this dispatcher module is basically handling such things. So suppose process P0 was executing, P1 came, and this process was of higher priority, whereas this process was currently executing. But because a higher priority process has came, so that is why this process cannot continue its execution as the scheduling was preemptive. So we are stopping this process. So when we are stopping this process, that means first of all, uh, before the control is transferred on to another process for execution, some exercises need to be performed in between. So one of them is that we need to save the state of the currently executing process. That is, the process control block in whatever state it is at that time when this process P0 was executing and it was stopped, that state is saved. Then we need to reload the state of process P1. So first of all, the process is stopped, its state is saved, then we are reloading the state of the process P1, and once this entire thing is done, then only the CPU will be able to work on on the process P1. So before it starts working on process P1, and at the time when the process P0 was stopped, this phase is referred to as a dispatch latency. That is time it takes for the dispatcher to stop one process and start the another process. So during this phase, these two activities are done. So whatever amount of time is spent on these two activities, this is referred to as dispatch latency. I hope you got the point. So now let's discuss about the scheduling criterias. So if you see over here, basically I have told you earlier that we are having variety of scheduling algorithms, and these algorithms are having different properties, and the choice regarding which algorithm should be used, it basically is not like that every algorithm is favoring every category of processes. So a choice of a particular algorithm may favor one class of processes over the other. So there are certain criterias which are taken into consideration when we are selecting a particular CPU scheduling algorithm. So those criterias include, the very first thing is CPU utilization. So as far as CPU utilization is concerned, the sole aim over here is to keep CPU busy for the maximum period of time so that we can get maximum efficiency out of the system. So we want to keep CPU busy as much as possible. Second thing is throughput. Basically, throughput means that the number of processes which are completing their execution in per unit time. So more is the throughput, better is the system. That is, in per unit time, if more number of processes are completing their execution, that means we'll be having high throughput, and high throughput basically means a better system. Then the next criteria is turnaround time. It basically refers to the amount of time to execute a particular process. Within what span of time a particular process has done its execution, that is referred to as a turnaround time. The time which the process spends in the ready queue is referred to as a waiting time. So we want that the waiting time for a process should be minimal. Similarly, we also want that the turnaround time for a process should also be minimal. Then the next thing is the response time. It is the amount of time it takes from when a request was submitted until the first response is produced and not the output. What I mean to say over here is, suppose the process was waiting for CPU in the ready queue, and it got access of CPU at some point in time. So during this phase, when this process got the access of CPU, it executed for some time, and it because of some reasons it has to come back to the ready queue again. So as far as response time is concerned, it is regarding the first time when the process gets the access of the CPU. It is not about the completion of the entire job. So as written over here, amount of time it takes when a request was submitted until the first response was produced. So when this process got the access of CPU for the first time, that is basically referred to as a response time. It is not about its complete execution. Suppose this process is coming to CPU for 3-4 times, we are only considering the first entry of this process from ready queue onto the running state. So that is called the response time. So now if we see the scheduling algorithms optimization criteria, so I have already told you over here that we want to have optimum output from our system. So in that case, the optimization criteria includes we should have maximum CPU utilization, we should have maximum throughput, but we should have minimum turnaround time, minimum waiting time, as well as minimum response time. Now, over here, I would tell you some of the terminologies which are, in fact, which will be used when we'll be um, uh, going through the various CPU scheduling algorithms, and those terms include the very first term is arrival time. So, arrival time is the time when the process enters the ready queue, that is, it has entered the ready queue and is waiting for its turn to get the access of CPU. The moment it enters the ready queue, that time is referred to as a arrival time. So at one time multiple processes can enter the ready queue. So if multiple processes are entering the ready queue simultaneously, so their arrival times will be same. Otherwise, different processes may enter the system at different times. So accordingly, their arrival times will be different. Then the next important term over here is the burst time. So as far as the burst time is concerned, it is also called execution time, as well as it is also called running time. So it is that amount of time for which a CPU is required by a process to complete its execution. Generally it is in milliseconds. Fine. And I have already told you the burst time is also referred to as execution time as well as running time. Then the next thing is completion time. So it is the time when the process has completed its execution. That is, it will be now into the termination state. The moment it completes the entire task which that process was supposed to do, so that moment is basically referred to as a completion time. Then we are having turnaround time. So we have discussed about turnaround time in the past. Now the question arises that how we can calculate the turnaround time. So to calculate turnaround time, if we are aware about completion time and the arrival time, we can easily calculate the turnaround time. So turnaround time is completion time minus arrival time. Fine. Similarly, we are having waiting time. We have read about this thing in the previous slide. If we want to calculate the turnaround time, the waiting time, so for that we should be aware about the turnaround time as well as the burst time of that process. So suppose the turnaround time for a process was 15, the burst time of a process was 7, so 15 minus 7 equals to 8, that is the waiting time. So we will be using these terms in all the scheduling algorithms which we'll be discussing in the coming slides. So these terms are quite important from that point of view. So let's move on to the next slide now. So these are the various scheduling algorithms which we'll be discussing in the coming videos, and those algorithms are first come first serve. Then we'll be discussing about shortest job first scheduling as well as shortest remaining time first scheduling. We'll be discussing about preemptive as well as non-preemptive cases. Then we'll also be discussing about priority scheduling as well as round robin scheduling. So in the coming videos, we'll be discussing about all these scheduling algorithms. Thank you.